Hi, welcome to my tutorials. Today's video will briefly show how is an electrical circuit diagram solved using nodal analysis. This will include the more difficult to deal with circuit diagrams if this method is used. So, what are the steps that need to be remembered when using this? Before that, actually nodal analysis is like a shortcut or the maximizing of Kirchhoff's current law. It is like the opposite of mesh method because mesh method is maximizing KVL in solving electrical circuit diagrams, but this nodal analysis is like maximizing KCL to solve for the unknowns in an electrical circuit diagram. So going back to the steps, the first step is to assume current direction in each branch. That's what is the first step for so when using Kirchhoff's current law. The next, select a node as the reference node. And for the rest of the non-reference nodes, you will assign voltages, where the voltages are referenced with respect to the reference node. This means that at the reference node, our voltage now is 0. And for the non-reference node, we are assigning voltages. So for mesh method, we are assigning loops as loop currents, but for the nodal analysis, we are assigning nodes as node voltages. Next, since we now have current direction in each branch, we will apply KCL to each of the non-reference nodes. Apply KCL. But instead of using I1 plus I2 equals I3 equals I4, something like that, we express those currents using Ohm's law in terms of node voltages. So of course, current is assumed like an arrow. There's a tail and there's the arrowhead. So current is expressed as the voltage found at the tail of that arrow minus the voltage at the head over the resistance that you can find. Next is use your calculator to solve for the resulting simultaneous equations. So proceeding with the example, find Ix with a given circuit diagram. So first step again is to assume current direction in each branch. So for this branch, that's okay already. For this branch, it's all right. It's okay already because we have here a given Ix. For this branch, we have a current direction pointing to the right. And for this branch is also good. But for the others, so for the 4 ohm resistor, for this one, what do you think is the direction for current? So let's just assume that this is going here. And then for this another 4 ohm, let's just assume that this is going downward. And for this one, let's assume that this is also going to the right. Now, next step to assumption of currents is we choose a reference node. And it's obvious we have here the ground. The voltage there is 0. So this node will be our reference node. And on this node, our voltage there is equal to 0. And for the other non-reference nodes, we assign voltages. So again, if for mesh, loops are loop currents. For nodal analysis, nodes are node voltages. So this node with label 1, so let's just name that as V1. For this node, let's name that as V2. And let's name this as V3. And this means, guys, that this V1, that is V1 volts. So from this point, this is the negative, and that will be the positive of V1. So at this point, this is positive V1 volts, and at this point, that is also positive V2. So this is the negative terminal for V2, and that is its positive. And also this one, negative for V3, and this is the positive for V3. Okay, next to that, we will apply KCL on each non-reference nodes. So applying KCL at node V1, KCL at V1. Again, instead of I plus I plus I plus I plus I. So we will express I using Ohm's law. What's the formula? V tail minus V head over resistance. So for V1, what's the current entering? We have this given already, 3 amperes. 3 amperes. And there's no more current entering, but we have there current leaving. We have Ix. And now guys, express Ix using V tail minus V head over resistance. So the voltage found at the tail of Ix is the non-reference node voltage V1. So that would be V1 minus V head. What's the voltage found at the head of that Ix? It's V2 over resistance 2. Another current leaving, we have this current, we have that current, and what's the voltage found at its tail? We have there V1 plus V1, and at its head, the nearest non-reference, okay, that is V3 over resistance 4. So this is our equation 1. And simplifying the circuit or the equation, we have, so I'll just continue on the other side. Okay, so guys, I'll be doing it this way. I'll be regrouping terms with V1, and it will be 1/2 plus 1/4 V1. Am I right? Minus 1/2 V2 minus 1/4 V3. So I don't like to calculate this because I think it takes time, but I have my calculator to solve for simultaneous equations with 3 unknowns. So minimizing calculation, just inputting this as the constant for your first unknown, then that's okay. And this will be our equation 1. How about for equation 2? So let's do KCL at node V2. KCL at node voltage V2. So what are the currents that enters V2? We have Ix, expressing that as V tail minus V head over resistance. That would be again the same as this one. Of course, that is Ix. So that would be V1 minus V2 over 2. What's another current? There's no more current entering, current leaving. This current, and that is V at the tail, it's V2, and V at the head is the reference node where V is equal to 0. So I'll just write that V2 minus 0 all over resistance 4 plus V2 minus V3. This current, I'm referring to this current, over 8. Now simplifying or regrouping. So we will have 1/2 V1, the terms with V2, plus we have here this negative 1/2 V2, and then this, then that one too, that is minus 1/4. I transpose it to the other side of the equation, and this one, so minus 1/8, or I could factor out negative. depends on you, V2. Then transposing this V32 to the other side, we will have plus 1/8 V3 equals, there's no constant, 0. And that will be our equation 2. How about for equation 3? So for equation 3, we will have KVL at, or KCL at node V3. And our equation would be current entering the current that passes through the 8 ohm resistor. So wait, I will erase some parts first. Okay, let's just do this. Let's just do it this way. So KCL at V3, we have the current on the 8 ohm resistor. We have there V2 minus V3. Tail minus head over 8. And we also have this current entering, that one, and that is plus, tail is V1 and the head is V3 over 4 equals 2Ix. Now, for our equations 1 and 2, our unknowns are V1, V2, V3. And if we include Ix, that would be the fourth unknown. And we need a fourth equation. But we know that Ix, when expressed in terms of V tail minus V head over resistance, is this one. Where is that? That is our Ix. So I will just substitute that to this Ix so that we will have 3 unknowns and we can use your calculator to solve for the unknowns. Okay, so this becomes V2 minus V3 over 8 plus V1 minus V3 over 4 equals 2 times this one. Of course, the 2 will be canceled out, so I will just write immediately, or I could write here to avoid confusion on your part, over 2. Then cancel out. So regrouping again all the terms with V1. So I will have here 1/4 V1, this one, 1/4 V1, and then the V1 on the other side is transposed to the left side of the equation, so that would be minus 1 V1. How about for V2? So we have this plus 1/8, and the other one, transpose it to the other side, to the left side, that would be plus 1, right? V2. And regrouping V3, we have this and this. So that would be, okay, I will factor out the negative part because I know all the terms with V3 are negative. This becomes 1/8 plus 1/4 V3 equals 0. And this is our equation 3. This is our equation 3. Now we have 3 unknowns, but we have these 3 equations. Inputting all of these equations to your calculator, then you can solve for V1 and V2 and V3. Okay, just input that. And then I will proceed here with the values for V1 and V2 and V3. V1, so V1 equals, V2 equals, V3 equals. So we have V1 as 4.8 volts. 4.8 volts. We have V2 as 2.4 volts. And we have V3 as negative 2.4 volts. Now to solve for Ix, we have again Ix as this one, V1 is V2 over 2. Substituting that, we will have Ix is equal to 4.8 minus 2.4 over 2 equals, what's the answer? Is 1.2 amperes. So our Ix is 1.2 amperes. Okay, that's it. Now proceeding with the next example. So what happens if our circuit diagram has voltage sources? So for the previous lecture, we have mesh analysis and we have current sources. Now we will do nodal analysis, but we will have voltage sources. Case 1, if a voltage source is connected between a reference and a non-reference node, we simply set the voltage at that non-reference node equal to the voltage of the voltage source. So for case 1, this will make it easier to solve for the unknowns in an electrical circuit diagram because the value for the non-reference node or the value of the voltage for the non-reference node is already given, which is equal to that voltage source connected between the reference and the non-reference node. Case 2, if the voltage source, whether it's a dependent or independent voltage source, is connected between two non-reference nodes. So this is a bit difficult, and that two non-reference node will form a generalized node. We call that supernode. If we have a super mesh, we also have a supernode. And we apply both KCL and KVL to determine those node voltages. So we will show you on what is the meaning of these statements with our next example. So we have this example. So as you can see, for case 1, there is a voltage source connected between the reference node. Okay, no. First step is assume current direction in each resistor. Let's follow the steps. But for this problem, the currents are already given. I1, we have here I1, I2, for this branch, and then for this branch, and then for this branch. And let's not just put current direction in these branches because there's only a voltage source found on that one. So now let's proceed to the next step, assign voltages. So we have here assign node voltages. So this is our reference node because the ground is there. And at that point, V equals 0. And we already have, at this node, we have V1, we have V2, and we have V3. Now, for case 1, it is said there, if a voltage source is connected between the reference and the non-reference, so set the voltage at the non-reference to be equal to the magnitude of that voltage source. So since this is negative, positive, negative terminal of your 10 volts and positive terminal, negative terminal, positive terminal, then our V1 is set to be 10 volts. Okay, therefore, this is 10 volts. Case 2, if a voltage source is connected between two non-reference, apply KCL and KVL. Or make that as a supernode. The connection of them is a supernode, 1. And then apply KCL and KVL to solve for V2 and V3. Let's call this supernode, if we have a super mesh called loop X, as you can remember. Let's call this supernode as supernode A. So to solve for the node voltages, let's apply KCL at the nodes. Okay. And the only node where we can apply KCL is this supernode A. Let's not just do KVL at this one because we have this voltage source. So the remaining node that where we can apply KCL is this supernode A. So let's apply KCL at supernode A. Current entering, what are the currents that enter this supernode? We have this I1 and express that using Ohm's law. The voltage at the tail of I1 is V1 and V1 is 10 volts. So V tail minus V head, which is equal to V2, right? All over 2 current entering. There is no more, no, there, supernode A. Current entering at supernode A, we have I1 and this also I4. This is already a supernode, guys. So I4 is also current entering at this supernode. So plus I4, Ohm's law, V at the tail of I4 of this series branch, it is V1 also, and that is 10 volts. 10 minus at the tail, that is V3, all over 4. Current leading, we have this I2 and I3. Express that using Ohm's law. I2 is V at the tail is V2. Minus at the head is 0. I will not just write that so that we'll have more space. Over 8 plus I3. What's the voltage at the tail of I3? We have that V3. Minus V at the head of I3. Okay, so at the head of I3, the voltage at the tail is 0. So minus 0, I will not write that, over 6. Now let's simplify or rearrange the terms. V2, I will transpose these variables to the other side, to the right side of the equation, and regrouping V2, we will have 1/2, this one, plus 1/8, this one, V2. And regrouping V3, we have plus 1/4 plus 1/6 V3 equals the constants. We have this 10 over 2 equals 5 plus 10 over 4. What's that? Okay, I will not simplify for you to know where did that come from. 10 over 2 plus 10 over 4. And this is our equation 1. Okay. We have two unknowns here, V2 and V3. Although we have their V1, but we already have the value of V1. So we need to solve for V2 and V3, and we only have one equation. Where can we get for the second equation? So as you can see, guys, V2 and V3, between them is this 5-volt voltage source. So how are you going to form the equation on that? Like I said a while ago, V2 is the voltage that is coming from this reference node to that point. And this is the negative terminal of V2, and this one is the positive. For V3, this is also the negative of V3, so that at this point, that will be a positive V3 volts. Now, this is V2, and this is V3. Now, we can apply KVL on this closed path. Let's name that loop X. applying KVL at loop X, we'll have our loop passes through the V2 source, enters the negative, leaves the positive, so that would be a positive V2. Then passing through this 5-volt voltage source, it enters the positive of 5 volts, then leaves the negative, so that would be a negative 5. Then it passes through the positive of, enters the positive of terminal of V3 and then leaves the negative, so that would be negative V3 equals 0. Arranging, we have V2 minus V3 equals 5. And that would be our equation 2. So using your calculator, you can now get for the values of V2 and V3. Okay, so we have V1 as, or V2 as 9.2 volts. Okay, I'll put this as a red one. 9.2 volts and V3 as 4.2 volts. Although there is no unknown in this problem, at least you have solved for the node voltages of this more complex circuit diagrams using nodal analysis.